Good afternoon. During the first part of the lecture of today, I will present a few results dealing with first and second order derivative of a curve. The first result I want to present is a proposition (1.18), which says that if gamma defined on the interval I with values in Rn is a curve with constant speed, then gamma prime of t is orthogonal to gamma second t for all t in I. In order to prove this result, I will use part 1 of proposition 1.17 we have presented last time. This proposition says that if you have a curve such that the length of the vector gamma of t for all t in I is a constant, then gamma prime is always orthogonal to gamma t. What we have to do in order to prove this result? Very easy. Apply proposition 1.17 to the curve gamma prime defined on I with values in Rn. Why? Because the curve gamma prime satisfies this hypothesis. It's written here. If a curve gamma has a constant speed, then the vector gamma prime has a constant length for any t in I. So you get immediately the result from here. You get that gamma second, which is the derivative of gamma prime, will be orthogonal to gamma prime for any t in I. The second result I want to present is a comparison between the length of a curve and the distance between its endpoints. Precisely, I will present the second part of example 1.19, named the shortest path between two points. So let's take a curve defined on a closed interval AB with values in Rn. The curve define P to be gamma A, Q to be gamma B. So in other terms, P and Q are the endpoints of the curve gamma. and let L be the arc length of gamma, that is the integral from A to B of length of gamma prime t dt. What we want to do is to prove that L is greater or equal to the length of the vector Q minus P. So let's start making a picture. So this is the trajectory of the point which moves according to this curve, and what we want to prove is that the length of the curve gamma is greater or equal than the length of the vector having its tail at P and its tip at Q. In order to prove this result, I will use the Schwarz inequality that I will recall here for you. It says that if x and y are vectors in Rn, then the absolute value of the inner product of x with y is smaller or equal than the product of the length of x multiplied by the length of y. Of course, if this is true, it is also true that the inner product is smaller or equal than this product here. And this is the inequality I'm going to use. Okay, let's set n to be the unit length vector given by q minus p over length of q minus p. The length of the curve gamma, as announced before, is the integral from a to b of gamma prime t dt, and this can be written as the integral from a to b of gamma prime a times 1 dt but this is also equal to the integral from a to b of gamma prime t times the length of n. This is a vector of length 1. T, and by the Schwarz inequality, this is smaller or equal than the integral from a to b of the inner product of gamma prime t with n. But this one, this integral, can be written as the integral from a to b of the derivative with respect to time of the inner product of gamma t with n. The equality between this integral and this integral follows immediately from the fact that n is a constant vector. Now it's very easy to compute this integral. You have the integral with respect, sorry, I forgot to divide it. So we have an integral of the derivative of a function with respect to the variable t integrated in dt. So this is a difference of gamma b multiplied by n and gamma a multiplied by n. But this is equal to gamma b minus gamma a times n. And now we use the fact that gamma b is q and gamma a is p. And we replace n by q minus p divided by the length of q minus p. And this is the length of q minus p squared divided by q minus p. And this is equal to the length of q minus p. And this is the end of the proof. Maybe some of you is thinking, how did you prove this identity? Very easy. I use the fact that the inner product of a vector x with itself is equal to the square of the length of the vector. The next result I want to prove is about the rate of change of the speed of a curve. Precisely, I want to prove the proposition 1.20, and in order to do this, I will introduce some notation. I will suppose as usual that gamma defined on I with values in Rn is a curve. then I reset V of t to be equal to gamma prime of t, and A of t to be equal to gamma 7. We already know that this is the velocity vector, and the second one is what we call acceleration vector. Proposition 1.20 says that the derivative with respect to the time t of the length of the velocity vector v of t is equal to the inner product of A of t with v of t divided by the length of v of t. I'm sure that you recognized what is this? This is the component of the acceleration vector in the direction the direction of the velocity vector. Let's prove it. Okay, so we first observe that the v of t is a square root of the inner product of v of t with itself. Consequently, d dt v of t is d dt square root of this inner product, and this is equal to 1/2 times 1 over square root of v of t dt product times d dt of the inner product d dt with itself. This is equal to 1/2 1 over length of v t times the inner product of v prime t with v of t plus the inner product of v of t with v prime t. By symmetry of the inner product, these two summands are the same, so this is twice v of t, v prime of t v of t, but v prime of t is a of t, and we get the following identity. We get 1/2 1 over v of t length times 2 a of t inner product, and this is equal to A of t, V of t divided by length of V of t. So, and this is the end of the proof. So this proposition says that if we take the vector A of t equal gamma second of t, and we decompose it as follows: A of t equal to A parallel of t plus A orthogonal to t, then where A parallel of t is parallel to Vt, and A orthogonal t is orthogonal to V of t, then this proposition says that the length of this vector is responsible for the rate of change of the speed, only the parallel part. We will return in the future to this topic, and we will see better what is the meaning of A orthogonal. The next topic of today is the reparametrization. Okay, suppose as usual that gamma defined on I with values in R3, sorry, in Rn, is a regular curve. Then we call trace the image of gamma that is gamma of I equal to all the values gamma t for t in I. So observe that the trace is a subset of Rn, of course, and it does not contain any time information. Different curves can have the same trace. Example. Gamma t defined by t squared with t into interval minus 2, 2, and gamma tilde t equal to 2t squared with t in minus 1, 1 have the same trace. It is the portion of parabola shown in this picture. So the endpoints have coordinates 2, 2, and minus 2, sorry, 2, 4, and minus 2, 4. The reason why this is true is that if we set phi to be the map defined on minus 1, 1 with values in minus 2, 2 as a phi of t equal to t, then it's clear that gamma tilde t is gamma of phi t, which can be also written as gamma composed with phi evaluated at t. We will say that gamma tilde is a reparametrization of gamma, and we refer to gamma and gamma tilde as two parameterizations of the same path. So this was just an example to introduce the idea of reparametrization, but let me give you the definition. So definition one point 22. So suppose as usual, that gamma defined on I with values in Rn is a regular curve. Then reparametrization of gamma is a function of the form gamma tilde equal gamma component phi defined on I tilde with values in Rn, where I tilde is an interval and phi defined on I tilde with values in I is a smooth bijection with nowhere vanishing derivative that is phi prime t different from 0 for all t in I tilde. It is possible to give a visual interpretation of this definition. So suppose that this is Rn. This is the interval I on which gamma is defined. So this is the map gamma, this is I. The definition says that the reparameterization of gamma is a function of this form here, where phi is a map from an interval I tilde with values in I, and gamma tilde is a composition of gamma with phi. This definition says that phi must have nowhere vanishing derivative. Let's see what is the consequence of this. Since phi has nowhere vanishing derivative, then the new curve gamma tilde is a regular curve, exactly as gamma. And let's prove this. It's a simple application of the chain rule. So since gamma tilde is gamma composed with phi, then gamma tilde prime of t by the chain rule is given by phi prime of t times gamma prime of phi of t. And this is different from 0, where 0 means 0 vector. So it's a 0 denotes the 0 vector. And this is true because gamma is regular. So this is a vector which is non-zero, and this is non-zero by hypothesis. Since phi prime is different from 0, then it has a constant sign. Phi prime different from 0 for all t right tilde implies phi prime positive for all t right tilde, and this means it is monotonically increasing. Or phi prime negative for all t right tilde. It is monotonically decreasing. So now we can give the following definition. 1.23, gamma tilde given by gamma composed with phi is orientation preserving if we are in the first case, that is phi prime is positive. It is orientation reversing if we are in the second case. Orientation means a choice of direction in which to traverse, to trace of a curve. Okay, let's consider one example. If gamma defined on I with values in Rn is a regular curve, then gamma tilde t defined by gamma minus t for t in the set of the values given by negative s with s in I is an orientation reversing reparametrization of the next result I will present shows that there exists a very special way of reparametrizing curves. Precisely, it is possible to reparametrize any curve, any regular curve, by Acklin. And this means that the length of the vector gamma prime is equal to 1 for any t in the interval of definition. Precisely, we have a proposition 1.25 which says the following: given a regular curve gamma from I defined on I with values in Rn, there exists reparameterization of it. Let's see the proof of this result. Fix E0 in I. And consider the arc length function S defined on I with values in R, given by S of t equal the interval from t0 to t of gamma prime of u length du. Set I tilde to be the image of S, so it is equal to S of I. Let's observe the following. By fundamental theorem of calculus, we have that ds dt it is equal to the function here evaluated at the upper boundary point of the interval t0 t. So it is equal to length of gamma prime t, and this is non-zero by hypothesis because the curve is regular. This implies the function S is a bijection and it is smooth because you can compute also the higher order derivatives and show easily that they exist. And of course it has a non-zero derivatives. If this is true, then S has an inverse. S has an inverse. Let's call it phi. So we have phi define on I tilde, which has been defined as Sy with values in I, which share the same properties as S, so this means that it is a smooth bijection and has nowhere vanishing derivative. Why this is true? Because this function is the inverse of this function here, which was smooth with nowhere vanishing derivative. You know from the course of calculus that there exists a formula giving you the derivative of phi in terms of the derivative of s. Okay, now let's define gamma tilde as a gamma composite phi defined on I tilde with values in Rn. It remains to show that this is a reparameterization of gamma, which has the property to have a unit speed. So we have to prove that it is parameterized by arc length. One way of doing this is to look at the length of gamma tilde prime t, which is the length of gamma composed with phi prime t, and by the chain rule this is the length of phi prime t gamma prime evaluated at phi of t. And what is this? This is the product of phi prime of t no need to use the absolute value because this is always positive, times gamma prime phi of t, and this is equal to what? We need the formula which gives us the derivative of the inverse function. Phi is the inverse of s, so phi prime of t will be equal to the inverse of s evaluated at phi of t times gamma prime evaluated at phi of t. But what is sorry, s prime. But what is s prime of phi of t? It's exactly this one. We computed it before. Unfortunately, I erased. But before we computed that the derivative of s coincide with gamma prime, and here we are evaluating s prime at phi of t, which is exactly what you have here. So the product of these two functions is exactly equal to 1. Okay, in the last part of the lecture, we will deal with a special class of curves known as closed curves. Definition: 1.26. We call closed curve a regular curve of the form gamma defined on A, B, with values in Rn, such that gamma A is equal to gamma B, and all derivatives match. That is, gamma prime A equal gamma prime B, gamma second A equal gamma second B, etc. If gamma is also 1 to 1, on the domain A, B, please observe that this is a set which is closed on the left side and it is open on the right side. Then gamma is called simple closed curve. Examples: this is an example of trace of a simple closed curve. These are traces of not simple closed curves. These are traces, traces of curves which are not closed. For which reason? The first one does not satisfy this, because gamma A is different from gamma B, and for this one you have that gamma prime of A is different from gamma prime of B. But gamma A, okay, let's write, even though and this point is gamma A equal gamma B. I would like to present an explicit example giving the formula for gamma. For example, gamma t equal cosinus of t sinus of t with t in 0 to pi is clearly a closed curve, which is also simple. It is a simple closed curve, and it is a restriction of another curve, let's say gamma bar of t equal cosinus of t sinus of t with t in minus infinity plus infinity to 0 to pi. This curve here is clearly periodic. Gamma bar is periodic. So we were able to construct a simple closed curve by considering the restriction to a smaller interval of a periodic curve. This is a coincidence, or it is always true? The answer is that it is always true. This is what this proposition says. A regular curve gamma defined on AB with values in Rn is a closed curve if and only if there exists a periodic regular curve gamma hat from defined on R with values in Rn with period B minus A such that gamma hat T is equal to gamma T for all T in AB. Okay, let's prove this. Suppose that gamma from A to B with values in Rn is a closed regular curve. Show that it is the restriction of a periodic regular curve gamma hat defined on R with values in Rn to all period B minus A. Okay, how can we construct gamma hat? Set the gamma hat of T equal to gamma T for T in AB gamma of T minus B minus A for T in B plus B minus A gamma of T minus 2B minus A for T in 2B minus A. Maybe it's a good idea if I raise a bit here, so 2B minus A plus B minus A and so on. And why this is the good definition? Okay, the first one, the first choice is clear because we are looking for a periodic regular curve gamma hat whose restriction to AB coincide with gamma. So this is a forced choice. What about the second line here? I made this choice, because if you evaluate this function at b, you will get gamma b minus a, and this is gamma a. So this means that this portion of curve gamma hat starts at gamma a, which is exactly the endpoint of the first piece of curve. And if I evaluate this function at b plus b minus a, I get gamma b plus b minus a minus b minus a. I get gamma b again. And if I continue, I get similar results. So this is a good choice. And the regularity of gamma hat follows from the fact that the gamma is close and regular. Now it remains to prove that there exists a periodic curve, a regular curve gamma hat from R inversing Rn of period b minus a, such that gamma hat of t is equal to gamma of t for all t in AB, then gamma from AB into Rn is a closed regular curve. How to prove this? This is very easy. We have to use this identity here. So gamma hat t is equal to gamma t for all t in a b. The regularity of gamma follows from the regularity of gamma hat. We have only to prove it is closed. So show that gamma is closed, that is gamma A equal to gamma B, but this is equivalent to gamma tilde A equal to gamma tilde B, and this is true because, for example, gamma tilde B can be written as gamma hat A plus B minus A. But this is the period of the function gamma hat So this is also equal to gamma f. Okay, that's all for today. Thank you for your attention.